The title of my lecture is Analogies and Categories, or Categories and Analogies. I planned to talk in detail, in some detail, of many analogies which I exploited because my work in category theory is more or less like experimental work. That is, look at many examples and try to find what makes them tick. I shall concentrate on one of these analogies, and if I have time, but I don't want to take more time than I'm allowed to take, I'll speak briefly about a few others. Now it's sad that Colin McClarty is not here, but that's how it is.
He's coming.
Okay, because I wanted to make a certain number of strong claims. By strong, I mean really strong, because we are not here in an ordinary mathematical meeting, but more or less has something to do with philosophy. And, well, it's good that sometimes in philosophy one makes a stand and says what he thinks. Okay. Yesterday, for example, Colin tried to convince you of something he had learned and understood from Bill Lovier, namely that one can more or less get rid of set theory, and by using, say, a topos with natural numbers objects, and if you want even to approximate even more set theory, you can suppose it Boolean, you can suppose it satisfying the axiom of choice, and you can suppose that it has a natural numbers object. So if you assume you are given such a topos, Bill and Colin, after Bill, said you can do all of mathematics. And of course, you can construct the reals, you can do all of analysis, all of whatever you want. Except what? Except the principle. Namely, you cannot do category theory. And for Bill, for whom category theory is very important, that seems to be something missing of primary importance. What do I mean by this? Well, suppose we start with such a topos, E, which we want to consider as the category of sets. So, the natural question which arises is, what kind of category theory one can make for which this E plays the role of sets? Can one say, for example, for a given category, C, that it has, say, products? For example, a complete category will have products indexed by sets. Can we say for a given category that it has products indexed by elements of E? seems a natural question. The answer is, with these data, you just cannot. It doesn't make any sense, starting with a category, to say that it has products. You can say that it has products of two objects, but you cannot say that if I is an object of E, think of it as an indexed set, a family xi indexed by I has a product. Why can you not say that? Because you don't even know what a family of objects of a category indexed by an object of E, you don't even know what that means. Okay? Let us even be, I want to show you very strange things, hoping that you will be convinced that from an epistemological point of view, category theory, unless you want to use universes, etc., therefore a lot of set theory and even elaborated set theories, axioms much stronger than set axioms. You suppose you have universes bigger and bigger, and the categories have to be elements of some of these universe. Therefore, they are sets of big size, maybe, but they are sets. And you claim that you don't need sets. You need even stronger versions of set theory to do category theory, or you seem to need. Okay, let's even assume we know what this thing means. Suppose we have a category such that every pair of objects X and Y have a product, and the category has a terminal object. Okay? So, what do you conclude? That the category has finite products. And the answer is just no. Because finite is not our naive idea of finiteness. In a topos, there is a notion of finite objects. Even if you have a natural numbers object, suppose you want to prove such a theorem, what will you say? We will make an induction on the number of objects. Who tells me that I can count the objects by the natural numbers object here? Nothing. One more thing, which cannot work. The natural numbers object, n, has a universal property, a la Lovier, defined with respect to objects and maps of E. The axiom of Lovier says it has a zero successor, and it's universal with this property, namely, given any x in E, any x0 in X, any f from X to X, there exists a unique map which makes this diagram commutative. But this says something about the universal property with respect to objects of E. What about objects of some extraordinary category which doesn't live in E? You cannot use induction. Of course, when you are using universes, you say that n has universal property for all sets, a category, after all, is nothing but a set, well, a set of maps and sets of objects, but a set in a universe, fixed universe, which is a set. Therefore, you can use the full induction for n with respect to all sets, and in particular the sets which live in such a universe. But if we are starting with a given elementary topos with natural numbers object, all we can say is that the natural numbers object has a universal property with respect to all things which live in here, not which live outside. Okay. Let us see even this in a more naive manner. Let us see this in a more naive manner. Suppose we do believe in set theory, which I don't, by the way. And since I said I was going to make some very strong claims, here is a claim. I sincerely hope, I might not see that during my lifetime, that someone will prove that set theory is inconsistent. That will not imply that mathematics will all fall down. Although people say mathematics, not category theory, let's say classical mathematics, are founded on set theory, I claim that this is not the case. Why? Well, to begin with, if you look at the activity of most mathematicians, 95% of them, perhaps even more, don't even know what set theory is about. 95% of them would be totally unable to write down precisely the replacement scheme or the comprehension scheme. Yet, they do mathematics. And they do, for some of them, very good mathematics. For some of them, outstanding mathematics. Because let me tell you that Grothendieck doesn't know set theory. And I have proofs of this. Set theory in the technical sense. So don't tell me that Grothendieck was unable to do mathematics because he didn't know set theory. So what kind of foundation is that? Which you can completely ignore in the field which is supposed to found and do work in this field outstandingly. Another thing, this is, again, I said I'll take strong stance, so I'll take strong stance. Why not? You look at set theory, and you look, for example, at the replacement scheme or someone which is simpler, namely the comprehension scheme. So it is a scheme. That means it is potentially an infinity of axioms. So take all the books of mathematics supposedly founded on set theory, which have been written, and all the books of mathematics which will be written, if mathematics still exists, 1,000 years from now. What can you immediately say? That only a finite number of axioms have been used. Therefore, one should try to concentrate on, you have these huge axiom schemes, one should try to concentrate on what is really useful in mathematics. Which instances are really useful? Here is another thing about sets, because I will need all that. Here is another thing about sets. You have to take the whole thing at once for granted. Otherwise, you cannot move your little finger. Let me make this precise. You do not assume that the product of two sets exists. It's not any axiom. You prove it by using the comprehension scheme or the replacement scheme. An instance of it that you prove. But let's look a little bit at what you really prove. If you want to construct, say, n cross n, natural numbers, this is axiom of infinity, you want to construct n cross n. If you look at the construction, which is given in all books of set theory, you have to construct this thing as something in the power set of the power set of n. Just to construct n cross n, which is countable, you have to go to the double power set of n, of which we know nothing. Because, say, for example, of Paul Cohen thing about we don't know how many cardinals there are between n and this double power. And you have to go all this to just make this tiny construction. This is just crazy. Unless you think that Zermelo-Fraenkel is God-given and you have to accept it, like not even the Jews accepted the Torah when it was brought to them. Okay, so let's look a little bit at some, I don't know how to erase this. Maybe I didn't use the correct, maybe I use another. Fortunately, I have one or two slides, not more, because I don't know how to use them. So I shall use one of the slides.
Is there any more paper on the flip chart which Sean could use if he wants to?
Is there another side to the blackboard?
Or would you prefer to use the flip chart?
I have mine, and I know that mine work. I tried to use one of the others, but I brought mine to be on the safe side. And I know that I can erase mine. And I even brought my own eraser. Okay. Ha ha. Ha ha. No, okay. Let me just put. Could you please just like this on, and I want to put this slide, which is page number 2, on, and be able to comment on it. How do you get light here? Don't tell me that even light does not work. Ah, good. Can you read me?
Yeah.
Okay. Okay. This is to prove you that you cannot prove that a subcategory of a small category is small. That's surprising. Small is a set. So a subcategory of a small category should by all means be small. The answer is no. If you believe that sets exist, take a model of set theory, a countable model of set theory. You can do that. What is a countable model of set theory? It's a set, because models are taken in sets, which we should not think of as a set, but the universe of all sets. It's a set equipped with a binary relation, which is the formal belonging, x belongs to y, which is totally to be distinguished from the membership relation which exists in the universe where we are taking our model. This is a formal membership relation. So I shall call a class, I want to make a distinction between classes and sets. To make very strong, but all this will still be in set theory. I shall call class anything contained in the model. I shall call this a class. Something contained in the model. Now, if I take any element of the model in the naive sense, it defines a class, namely the class of all x's in the model, such that x is a formal element of capital X. This is a class. I shall call these classes representable. Okay? And it's not by sheer luck that I call them representable. I have plenty of things in mind, analogy. So, I shall call a class representable, and you have to think of this as a class which is a set. There is a set, an element of n, such that this is a class of all formal elements of x. What does the extensionality say? So I call this x hat, okay? What does the extensionality axiom say? It says that the map which to each x in the model associates the class x hat is injective. If two elements, that's exactly the extensionality. If two elements of M have the same formal elements, they are equal. That's the extensionality. Okay. I shall call a class definable if there is a formula, maybe with parameters, of the language of set theory. And this is a very poor language. There is only formal membership and equality. Such that X is an intuitive member of D if and only if it satisfies the formula phi. And now we look at the comprehension scheme. The comprehension scheme, what does it say? Did I write it here? Yes. I prefer to think not in a syntactic manner, but in a semantic manner. What does the comprehension scheme say? Oops. Here it is. It says that the intersection of a representable class and the definable class is representable. Maybe you are not convinced by this, but if I have some x, one can, and a formula phi, one can construct a new set, a set of x, which are members of x, such that phi is satisfied. The set of all things which are contained in x, elements of formal elements of x, that is elements of x hat, and the set of all x which satisfy phi of x is D, if D is the definable class defined by phi. Okay. Well, now, suppose x, I'll draw again my model. Suppose x is a set, an element of my model. Here is x hat. All the formal elements of x. Okay? If I take something which is contained in x hat, something, sorry, y, class y, contained in x hat, I do not know that this y is representable. There is no reason, because it is not defined by a formula. If I look, say, at my first slide, here, if I take a red pen, which I hope I have, yes, and if I draw a red line here, somewhere, and if I tell you, look at all the y's which are to the right of the red line, that's not a set, because that's not defined by a formula. Now, suppose x is any infinite set. Infinite in any sense you want, because it will mean it has an infinity of formal elements. Okay? We look at all the classes which are contained in x hat. All the classes contained in x hat, that's the power set of an infinite set, it's certainly not countable. On the other hand, the definable classes, all of them are defined by formula, so there is only a countable number of definable classes. So this cannot be the same. So this gives you immediately a class contained in a set, but which is not a set. That's how it is. Unless you are working with universes, etc., etc., but who wants to work with universes? Okay. So, I wrote a paper in '81, but which was published in 85, which is called Fibered Categories and the Foundations of Naive Category Theory. And I want to make a few remarks about this paper. I like very much this paper. It's not because I wrote it. I read it when I prepared this talk. There is almost nothing I would want to change in it. I could add, because I have made progresses, but not change things which I say. So this is one reason. A second reason, totally different, is that I dedicated this paper to Grothendieck. I was never a student of Grothendieck. More, I met him only once. I dedicated to him the paper, and I'm very glad I did, because none of his former students, who owe him so much, had the decency to do this for any of their papers, which were directly inspired by the ideas of Grothendieck. So this is the second reason. And the third reason, it is in the Journal of Symbolic Logic. I'm not a logician, but moreover, this is probably the last paper ever which was published from handwritten notes. I cannot type mathematics. I sent handwritten notes, and the advisor told me it will never be published. Well, it was. And I'm sure it's the last. Not even typed, it's handwritten.
Was it written in English?
Sorry?
Was it an original, you wrote it in English?
You don't what?
Did you write it in English or you translated from French?
I can what?
Did you write the paper in English?
Oh, in English, of course. No, I wanted it to be written in English. That was no problem, but I could not type it. I had nobody who could. Now I have some person who is glad to, or makes me glad to type my papers whenever I give her papers to type. But at that time, I didn't have. I wrote it, handwritten. It was accepted and published. So here are a certain number of reasons why I like this paper. Okay. In this paper, I gave what I think are foundations for category theory. Setless foundation for category theory. I will try to explain, but it's a long and difficult paper. I will try to explain vaguely what these foundations are. I would be able to explain it much better if I had a decent blackboard or whiteboard, but that's how it is. But I would like to read, although it's a bit long, I would like to read the introduction of this paper. Since it's called Foundation of Naive Category Theory, I want to read the introduction. It begins like this. Any attempt to give foundations for category theory or any domain in mathematics could have two objectives, of course related. First objective, non-contradiction. Namely, to provide a formal frame rich enough so that the actual activity in the domain can be carried out without this frame and consistent, or at least relatively consistent, with a well-established and safe theory, for example, Zermelo-Fraenkel. So, consistency. Adequacy. In the following non-technical sense, and this is more important to me than consistency. Adequacy, what I mean by this? The basic notion must be simple enough to make transparent the syntactic structures involved. The translation between the formal language and the usual language must be, or very quickly become, obvious. This implies in particular that the terminology and notations in the formal system should be identical or very similar to the current ones. Although this may seem minor, it is in fact very important. I'm much interested in linguistics. Although, I'll skip a few points. Although it seems to have been the main preoccupation of the logicians who tried to give foundations for category theory, I'm only mildly interested in mere consistency for the following reasons. Categoricians have, in their everyday work, a clear view of what could lead to contradiction and know how to build safeguards. Second reason, if a formal system, because there have been huge complicated attempts to give foundations of category theory, if a formal system fails to satisfy too many of the adequacy requirements, adequacy must be simple, easy to handle, etc., it will be totally useless. I don't care about complicated foundations which I can do nothing with. It will be totally useless, and worse, the inadequacy will probably reflect too superficial an analysis of the real activity of categoricists. And I skip a few things. And the requirements of adequacy, in a sense, and here I come to the notion of analogy, etc., in a sense, force the method by which they can be achieved. Namely, a careful investigation of a linguistic type, both semantic, what does category theory talk about, and syntactic, how does it talk? This investigation should cover a sufficiently representative part of the corpus of category theory, again, analogy, and a good knowledge of category theory is necessary to find what is representative. The result of these investigations have to be accepted as they come out, however strange they or their consequences may seem. And there will be indeed some very strange statements in my paper, which will become quite natural in the adequate setting. The formal framework has to be constructed from these results and not forced to fit into any a priori determined, well-known structure. Because there are people who know, say, fuzzy sets, and whenever they want to formalize something, they use fuzzy sets. Others know whatever, they know that whatever, even if it doesn't fit. So it has to be accepted as it comes out. And I added, it will be the case that our approach fits into such a structure, well-known structure, namely the fibered categories introduced by Grothendieck, but this has to be viewed as an unexpected gift. It was a fact that it ended up in the domain which I knew very well, but could have ended up in something totally different. This is an unexpected gift because it permitted me to progress very quickly. It was a domain I knew. Okay, let me give another example. Nothing to do with the foundation of category theory. If I have time, I'll come back to it. Again, an analogy. A few years ago, I wanted to understand the word very. Not very, but very. Okay. What I came with was, you can say very, very big, and you say a little more than very big. You can say sometimes very, very, very big, and you say a little more. But you have the feeling that after a certain number of times, it doesn't add anything to add one more very. Okay? Moreover, the language, our language, is rich enough to give this limit of very. You would say, for example, he's really very big, and that's it. That very, 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 until it stops. Okay. So, you will tell me, well, that's very easy. You write V for very. And this phenomena means that V to the, there is an n, that's V to the n plus 1 equals Vn. Means after that you don't have to add something. Okay. Well, what do you do with this? If there is such an n, there is a smaller n. Okay? There is a smaller such an n. Will it be 2? Will it be 3? Can you tell me if it's 5? There is no, you know it stops, that there is no smaller time when it stops. That means what? That means that if you want to axiomatize this idea, the natural numbers should not be well ordered. Okay? Well, the natural numbers should not be well ordered. Okay, I say it. In purposes, natural numbers is not a well ordered object. So we look at toposes. But that was the first step, because I was telling you about a very thorough linguistic analysis. That was the first step. The second step was the following. I can go to my butcher or my whatever and explain to him this phenomenon of very. And he will understand very well that after a certain number of times, it stops. No need to say one more very. He can understand that perfectly. Does he know about natural numbers? Certainly not. Let alone natural numbers in a topos. So one has to be able to do that without natural numbers object, because it's typically of a finitary type. Okay? That was the analysis. And that led me to write a paper, a joint paper with the young students who helped me to prove a few things, which had nothing I was ashamed, I would have been ashamed to say, you have written this from very. I wrote a paper which was called Orbits and Monoids in a Topos, which was accepted and considered a good paper by Bill Louvier. I never told him that my motivations were axiomatization of Very. What does that mean also? It means the following, of which I am very much convinced, that mathematics have progressed very much by trying to understand and solve problems in physics, theoretical physics, or chemistry, or whatever other science. Maybe it is high time to complete the origin of interesting mathematical problems by seeking them in linguistics, in philosophy, in other domains, not the hard sciences. Here is an example. Okay. And this paper, by the way, has been published in the Journal of Pure and Applied Algebra, and the referee was Bill Louvier, and I met him at a meeting, and he told me, it's a very nice paper, how come you had this idea? I never told him it was about Very. Okay, let's come now back to the original question. How to do category theory without sets, by replacing sets by an arbitrary elementary topos. The answer is even more surprising than that. You don't need an elementary topos. It's much too strong for what you want to do when you do category theory. That is much too strong. Any category, say with finite limits, will be enough to go very far. But what is needed is another ingredient. Namely, you must give yourself some information. What information? Extra information do you need? Not just the category, the topos if you want, the base sets if you want, and a category. You must give yourself axiomatically the information of what is a family of objects of the category indexed by an object. This you have to give yourself axioms on this. Why don't we do that? Because we think that in set theory, if you will start with a category, you know what a family of objects of the category indexed by a set is. Well, you don't, unless the category is a set, big set, but otherwise the notion of what a family of objects of a class, category is a class, indexed by a set, it has no meaning. But we pretend that it has meaning. So we don't talk about it. But this process of eliminating sets has two, it turns out that it has two different results. One is to eliminate sets, which I'm very happy about because I told you what I think about sets. But another is to understand the role of sets. Since when we deal with sets and classes, etc., sets play a role, what kind of role do they play? How do they work? What makes tick this information about family? So, the information you need is Thus, not to give yourself a bare category and your topos of sets, but to give something which is a category equipped with a notion of family of object indexed by an object, by a set, by an object of our sets. You need this information. And when you have this information, then you can start working. You can start saying what is a category with products or et cetera, et cetera. But if we look at this way, and we try to understand a little bit more the role of sets. The category of sets has fabulous properties. But some of them are merely tautological. Because when we talk of families, we are of objects of a category, we are comparing the category with sets. And now if we compare the category of sets with itself, no surprise that it has many properties. Because any category with finite limits compared with itself by this process will have this fabulous property. We are doing comparison just as, say, the identical map between anything, whether they are topological spaces or rings or whatever, has always fabulous property because it's the identity. Not because we are dealing with rings or with topological space or whatever, because it's the identity. So we are comparing sets with themselves. There are some tautological properties which would be true when you compare any category with itself. Any. Okay. But there are some which are not tautological. And again, this is interesting because it tells you what specificity have sets. Okay? What are the non-tautological properties that the set have, which are not satisfied which they have when we compare them with themselves, which are not satisfied by any old category. Okay, how long do I still have?
15 minutes.
How many? 15 minutes, okay. Okay. Here are a certain number of questions which one should immediately ask. Suppose I give correct definition of, let's call a vibration over a base, the notion of a category with the information of families of objects of this category indexed by, that's vibration. Okay. If we look at some very simple question, take a topos. One can define the category of groups of the topos, or any algebraic structure, etc. I have given a general definition of a category having products, arbitrary vibration having products. So I can ask, is it true that the category of groups of a topos have products indexed by any object of the topos? And the answer is, as it should be, yes. You can ask the same question, because I've defined also co-products. Does the category of group of a topos have co-products? And the answer is, of course not, unless the topos has a natural numbers object. Because we know that if we look, say, at the topos of finite sets, you take two groups, two finite groups, well, what was used, the free product does not exist because you have to construct it by. So this becomes quite clear and natural. If the topos has a natural numbers object, then the category of groups, the category of rings, the category of whatever you want will have coproducts. Without the assumption of the natural number object, this category of groups, category of rings, etc., will have products. Infinite, by infinite I mean indexed by any object of the base category. Okay. I feel like I have my hands cut, but well. Let's look at yet another question. Usually, when people talk about categories, even in the most naive manner, you choose a universe, etc. So the category is a member of a big universe, and you assume that the category is locally small, which means that given two objects, their home is an element of the smaller universe. Can this, we know the importance of this, can this be also described for the general fibrations? And the answer is yes. Descriptions are here, so if you are really interested, you can find them. The answer is yes. But not only it is yes, but this is it's not clear in set theory that local smallness is very important. How is it? Well, size, things. It turns out to be a very important property, which can or cannot be satisfied when you replace it, say, by an arbitrary topos. If a fibration is locally small, this implies lots of other properties. Just the mere fact that it is locally small. Here is another question. Suppose we work in a naive category theory with sets, universe, whatever. And suppose I have a family of maps, Fi, say from xi to some y, indexed by a set I. Without thinking a moment, you will say, if I have this family of maps, I can define a subset I prime of I by just saying I prime is the set of all I in I, say, such that Fi is a mono. I can select among all these maps those which are mono. Well, well, well. No, you cannot. Unless you are working in categories which are sets. Why can you not? Because this is a honest to God set. So you try to apply the comprehension scheme, but the comprehension scheme can be applied only when you look at the formula of set theory. But this is not a formula of set theory. To say that Fi is a mono means for all G prime, if Fi G equals etc., then G equals G prime. You quantify over what? over pairs of maps of a class. Arbitrary, after all, the category can be very complicated. So you just cannot do this. Or Fi is an epi, or Fi is an iso. You cannot do that. And yet you do it. Well, of course you do it, because you need it. Of course you can do that inside the big set theory. But if you need it and cannot do it, you will have to put this as an axiom on the category. Category, I say that monos are definable if one can make this construction. And it's a very important notion, but which does not follow from the rest. Oh. Well, what does these kind, there are many other things to say that some formulas which are not set theoretic formula define sets. And I call this definability in vibration. What does it mean? If we are not formalists, try to understand what all this means. It means that we have our category of sets, topos of sets, whatever you want. It doesn't have to be a topos. And we have a fibered category, that is category with the notion of families. And to say that such and such notion is definable, what does that mean? It means that our category of sets understands some of the things which are going on in the big category. It understands what a mono means. It understands, etc. It's all as if being a mono can be added to the language of set theory and used with a comprehension scheme. So understanding is again something which makes sense and which has to be used if you want to do things. Maybe, and then you can try to prove that if G is the category of groups of the given topos, well, the topos understands because it's groups in this topos. But if it were any other thing, there is no reason why the topos would understand what is a mono in this abstract thing. If you have any question or remarks, I'll be very glad to answer. So define all these notions. Of course, Grothendieck invented fibered category, but all these notions are mine because he did never think of a fibration as something which represents families. Okay? So definability is something very important. And if you have to put these as axioms, unless the category you are working with has been built from the topos itself. Topos understands itself and understands the things which were very simply constructed from itself. But it will not understand abstract things which have nothing to do with it, unless you put this as an axiom.
As far as I understand, there's strategy, say, of Bill-Lavie of category of categories, right? And even wider, say, of internal categories. It's exactly that.
Again, the category of category, this doesn't work as he thinks. To say that the category of category has infinite limits, etc., etc., what does that mean? You have to refer to sets.
So you don't say it. You say it's strictly enclosed.
Sorry?
So you don't say it has infinite limits, you say it's strictly enclosed.
Here, for example, the situation is such that here is the challenge. Take any theorem of category theory, any, and I know some of them, okay? Take any theorem of category theory and replace categories by fibered categories and sets by given topos, whatever. And of course, put the relevant definability conditions, which you always assume without even talking about them when you do naive category theorem, meta theorem. I can prove that theorem. Hey!
Just if I'm quite agree with your analysis when you say that this classical, I don't know, classical Beal's approach is kind of tautological, but then you say something wrong about that, right?
About what?
About this kind of tautological nature of category approach. Yeah, when you say we just recognize what is there.
That these axioms are the category of small categories in sets, and they are satisfied.
But what is exactly wrong about that approach?
It's not wrong. It's just that some of these axioms don't make sense at all if you look at the fiber category over a given topos, etc., etc. Here is another thing, which there are so many things, I don't want to forget the important ones. Suppose our great-grandchildren will learn topos theory in kindergarten, which I hope they won't, by the way. Suppose that. Now, you know, I know, at least the people who know topos theory, that the good morphisms between toposes are geometric morphisms. Why? Why are they those? You could argue, we know this from geometry because toposes are toposes of sheaves, and we know this from geometry. Is there any reason internal to topos theory, knowing nothing about where topos theory came from, which would justify the consideration of geometric morphisms and not of logical morphism, which preserve the omega, etc.? Why is it the case that geometric morphisms, not looking at the origins of time and space, but now you know what the topos is? And the answer is yes, if you think in terms of vibrations. If you go out of just topos theory, but think in terms of vibration, they are completely characterized by preserving the local smallness, etc., etc. So, how shall I say? Topos theory is, say, set theory, suitably generalized. Okay, we know that set theory is important. But this is category theory, not just set theory. This is category theory without sets. Maybe I stop now because there might be questions.
Well, there are a lot of things that that one could.
Let me just put my earplugs so that I can hear you without. Sorry. Old age and maybe having spoken too loud and made myself self-deaf. Okay, one is enough.
Well, first, let me apologize. I didn't get back in time for the start of the session. I was supposed to chair, but I mean, there's a lot to talk about with this. But let me start with the one thing that first hit me when you said that Grothendieck doesn't know set theory, but Grothendieck has written down axioms for set theory.
Sorry?
Grothendieck has written down axioms for set theory when he defines a universe.
No. He defined universes in set theory, which he supposes known.
No, but he gives the axioms.
The axioms of universe.
But also axioms for set theory. He describes them in the appendix.
Okay, maybe. Well,
Yeah,
did he write the replacement scheme, etc., etc.
Yeah,
formally?
yeah.
I don't
And in
remember
fact,
that
I was a
he
little
did.
disappointed with this because I wish he wouldn't use
I don't
replacement.
remember that he did.
But,
But this changes nothing.
No, it doesn't.
Let me tell you why. Let me tell you why. Because, as I mentioned in other places, the worse he wrote à la Bourbaki, the worst book on set theory which was ever written and which will ever be written is the Bourbaki Théorie des Ensembles.
Oh, I don't know.
It is the
Have you
worst.
looked for all the worst?
It is the worst. No one understands the notion of a model of set theory.
Yeah.
No one understands what's the significance of replacement scheme or comprehension scheme.
Yeah.
There is a nice, tiny little book by André Krivine, which is called Théorie axiomatique des ensembles.
Yeah.
Few pages.
Yeah.
That's perfect to understand what set theory is about.
Yeah.
That's the one I used when some years I was asked to give a course on set theory. Certainly not Bourbaki.
Yes. I could agree with you that it's the worst important book on set theory that was ever written.
Sorry?
It's the worst important book on set theory that was ever written.
Okay, well,
But there are very bad books
the
you've
more
never heard
important, the worse it is.
of. Yeah. But you're right, but it finally changes
Especially
nothing.
since it came with all the aura or what of Bourbaki and influenced people in seeing set theory in a completely wrong manner.
But you're right, because I mean, if we want to do category theory over a topos as base, this is absolutely, I would agree with you.
Yes,
This is
but
the way to do that.
the thing is, you said, and Lovier said, that when you have toposes, you can do all mathematics, and I claim you can do all classical mathematics or whatever, but you miss what he considered as the most important. You miss category theory.
Well, actually, when I hear Lovier say that with a topos you can do all of math, I'm thinking that's with the apparatus of fiber categories over that topos.
Well, he didn't.
Yeah.
He did not invent and
No.
whatever fiber categories, or even was aware of all the developments which have taken place since I invented this aspect and developed it.
Yeah. What are the best references? I mean, you have not finished your book.
I'm probably not going to finish my book because I would have finished it if the very detailed notes of Voisin had not been circulated all over the world, and I have many more interesting things to do than to write in detail a book of which all the specialists know the most. Especially, there is a whole chapter on fiber category in Francis Borseux handbook, which is completely, and he says that, taken from the courses I gave there and my notes, Voisin notes, etc. So I'm going to what? He did even something worse. Namely, he couldn't do all in this chapter. There were many other interesting things which I gave in my course and which are in the Voisin notes.
Okay, yes.
So if he didn't have the space, he gave them as exercises.
Yeah. So that's what I wanted to ask. What's
So
the
what's
reference?
left?
So you feel that there are
what's
no good
left?
published references, but the Voisin notes are the place to go. Okay.
And the Voisin notes are 1981. And everybody knows them. Everybody who is interested in the subject knows them. They have been widely circulated, Xerox, etc., etc. I don't know how many hundreds of them are all over the world. I'm not going to write a book just, especially since I have other things which were not in the xuan-gottfried, and I have a new, this was one of the analogies I wanted to talk about, but I won't have time, something much more general than fibered category, which I call foliated category, and which is beautiful, just beautiful, not because I invented it, but because it's just beautiful. It makes fibered categories as a very, very special case, but the proofs are almost simpler in the general case than they are in the special case.
But there's no published reference on this, right?
I have this, I have talked very little about it. I plan not to talk too much about it and to write it down.
Thank you. If I just can also allow a remark, just me seems very, very interesting what you are doing, because it seems probably not in very technical terms, but it really looks like a different alternative approach to categorical foundation. How I understand what is the difference is correct, probably if you could comment on it. Say this Lavier's category approach is kind of classical in the sense that exactly as you mentioned in the beginning, we are trying to look, we regard, say, the category, a category of category, okay? And then we just define, like in abstract algebra, right? We define what is already there. So in terms of global structure of... No, I'm talking about Lavier.
It's totally different.
Okay, just finish. And how I understand the meaning of fibration as foundation, which, by the way, in Bourseau book, he just doesn't touch upon this point. He developed technically fibered categories, unfortunately. So, because you're always trying to say, okay, we need something outside. We say outside, right? And that turns the whole business of foundation and kind of relational. It's certainly it's not reduction. You can't say that you
No,
reduce,
I'm not saying we need
category
something
to base
outside.
category.
I'm saying we need, on the contrary, something which is not simply a category. A category need not be a set, okay? But sets, whatever we call sets, have to be able to talk a little bit about the category.
What I mean, but your picture, you say, okay, this is topos, this is category, so we can something define in topos, but not in that category, right? Which is, it's actually, you mentioned it inside, outside, at the beginning of your
Yes.
So we should bring something, like families, okay? We need families.
We need
shouldn't
families.
Talk about, right, we shouldn't talk about them naively, right?
But we need families, but that's very far from being enough. I mean, families, fibered categories were invented by Grothendieck, but his view and the reason is not that Grothendieck is, of course, I dedicated my paper to him, but he invented them for a specific purpose, for descent, for things like that. But he never realized that if you looked at them in a different manner, you could do, for example, Grothendieck invented toposes. He never realized that in the topos he invented, there was the object omega. He was absolutely enthusiastic when he found, due to Lavier, the object omega, and he calls it the Lavier object. So he was doing toposes for the purposes of algebraic geometry, and Lavier, that was his genius, realized that they were variable sets or whatever generalizations of sets. And this is, again, a proof that Grothendieck was not a logician. He did not know set theory. He would have invented or discovered the object omega.
Je vais parler en français.
Oui.
Il me semble que le terme d'analogie revient souvent dans votre œuvre, en tout cas dans votre pensée,
Oui.
et pas seulement dans l'exposé d'aujourd'hui.
Oui.
Et je voudrais savoir comment vous l'articulez avec la théorie. C'est-à-dire, est-ce que l'analogie sert de support à l'invention et à la création d'objets ou de concepts, ou est-ce qu'elle sert d'illustration après coup à des concepts qui ont été créés dans un autre registre?
Pour moi, en tous les cas, je ne dis pas qu'elle n'a que ce rôle, mais le rôle essentiel dans mon travail a été de m'inspirer quels étaient les bons axiomes, quelles étaient les bonnes structures, etc. Je faisais, comme je l'ai dit souvent, de la théorie des catégories expérimentale. Je connaissais pas mal de théorie des catégories. Je voulais essayer d'élaborer telle ou telle nouvelle structure sur les catégories, les bicatégories, les machins comme ça, j'en ai fait beaucoup. Hein. Et je testais les axiomes auxquels je pensais sur des exemples très différents les uns des autres. Et si ça marchait dans des exemples très différents, je me disais, c'est qu'il doit y avoir un substrat commun important. Voilà. Par exemple, voilà un autre exemple d'analogie. Lovir m'a appris ou m'a convaincu, il y a très longtemps de ça, en 70, que les topos, c'était une bonne façon de voir les ensembles. Bon, des ensembles généralisés. Alors je me suis dit, mais bon, si les topos, c'est les ensembles, ou des ensembles, on devrait pouvoir utiliser le langage de la théorie des ensembles pour les topos, qui ressemble tellement aux ensembles. Et j'ai élaboré ce que j'ai appelé le langage interne des topos, sans lequel maintenant on ne peut pas faire grand-chose dans les topos. Essayer de faire de la géométrie différentielle synthétique à coup de diagramme, ça sera totalement impossible. Mais donc, je me suis dit, ça ressemble au topos. Eh bien, voilà. Faisons que la syntaxe ressemble aussi, faisons que le langage ressemble aussi, et j'ai introduit le langage interne des topos, qui est très semblable au langage des ensembles, parce que les topos étaient analogues aux ensembles.
Merci.
Bon, je voudrais parler en français.
Oui.
Tu nous as dit que tu voulais t'ouvrir, enfin que il était temps de s'ouvrir à d'autres domaines. Tu nous as mis un peu l'eau à la bouche en nous donnant quelque chose qui semblerait être l'axiomatique d'une future théorie qui recouvrerait tout ça. Est-ce que si j'ai bien, enfin une grande partie de tout ce qu'on connaît.
Oui,
donc je comprends qu'il n'est pas utile effectivement d'écrire un livre sur les catégories, parce qu'il serait plus opportun d'écrire peut-être 3 pages sur cette nouvelle axiomatique. Est-ce que j'ai bien compris?
Non, tu as pas tout à fait bien compris, parce que, si tu veux, il est très facile, quand tu prends une théorie qui est déjà bien élaborée, d'écrire en 3 pages des démonstrations, ou même pas des démonstrations, des résultats nouveaux et, si possible, intéressants, importants, difficiles, etc. Mais quand tu es en train d'élaborer quelque chose qui est radicalement nouveau, il faut, qu'on le veuille ou non, pas mal de définitions pour fonder le domaine dans lequel on est en train de parler. Et les résultats ne peuvent venir que après un certain nombre de définitions, cascades, etc. C'est triste, mais c'est comme ça. Enfin, c'est pas triste, c'est les choses comme elles sont. Et par conséquent, si tu écris 3 ou 4 pages, tu n'auras rien comme résultat. On se moquera de toi, c'est tout.
Bon, donc j'ai presque tout compris, sauf qu'au lieu de 3-4 pages, c'est plutôt un livre, ou enfin quelque chose de plus conséquent.
Mais c'est comme ça. Si c'est un domaine vraiment nouveau, c'est comme si quelqu'un inventait la théorie des topos maintenant, qu'on ne connaissait rien aux topos, et que tu lui demandais d'écrire en 3 ou 4 pages ce que c'est que les topos. C'est pas possible.
Désolé pour les 3 ou 4 pages.
Non, mais c'est pas... Je préférerais n'avoir que 3 ou 4 pages à écrire. Ah, là, je les écrirais.
Moi aussi.
Pour en écrire, j'écrirais quand même 3 ou 4 pages volontiers.
Ok. Merci.
Oui, c'est une question qui concerne les philosophes, les questions d'analogie, à travers j'espère que les philosophes ont apprécié votre passion philosophique. Moi, me fait penser à une scène fureur héroïque, comme aurait dit Giordano Bruno. À propos de l'analogie, est-ce que vous concevez plutôt l'analogie avec, comme dans l'idée d'un recouvrement parfait de l'analogone et de l'original, ou est-ce que vous voyez l'analogie comme laissant une espèce de résidu, de différence, qui pourrait être la trace de l'opération du passage du modèle à l'analogique, et qui serait en même temps ce qui permettrait un peu une espèce d'écart inductif qui vous permet à vous de résoudre un certain nombre de problèmes à travers cette opération d'analogie sur des champs nouveaux.
Je vais essayer, c'est pas très facile que vous me posez, et j'ai posé ce type de questions, mais moi, en tous les cas, comme utilisateur, ce n'est pas une analogie qui m'importe, c'est le fait qu'il y ait plusieurs analogies, au sens le plus naïf du terme, pas philosophique, mais entre des domaines différents, qui me fait concevoir que peut-être tout ça a un dénominateur commun qui serait l'essence de ce à quoi tout ça est analogue. Voilà.
It certainly seems fair to say that you have changed the idea of indexed family by your fibered categories. The old naive idea of indexed family is somehow more sophisticated. You have changed the idea of indexed family.
I never used indexed family.
No, but you've changed my conception of indexed family by your concept of fibered category.
Oh, but that's not due to me.
Well, so your analogy has left a trace on me.
No. It's the thing is, I tried for 20 years to convince people who were doing index categories that fibered categories were better. But let me just finish. The thing is that both notions were invented by Grothendieck. He first invented what has now come to be called indexed categories, which he called pseudo-functors, never mind. And, well, less than 1 year later, he said, this is not intrinsic. The correct definition is, and he gave the definition of fibered category. So it was already, and I can grant you that if Grothendieck said that, you can trust him to be right.
But I mean, just the naive idea of a collection of objects indexed by I.
Yes.
I mean, of course, Grothendieck changes it some, but you also changed it some with your foundational approach to fibered categories.
But it was always my foundations and my work on was always on fibered category.
Yes.
Not on index.
No, but I
because
mean,
index is not intrinsic. Even if in a naive manner, I tended to think, okay, let's imagine that there is indexing, etc. But the intrinsic thing is fibered category.
But that's exactly the change.
Yes.
So,
No, but I never used indexed categories. Never.
no, but when I read, say, Kelly's topology, and he talks about, consider a set of topological spaces, T sub I, indexed by a set I read that differently because of having read your Journal of Symbolic Logic article than what Kelly could possibly have meant.
Oh, the one which I just, okay.
Yeah.
But well, since you mentioned this, my own vision of many things have changed. Even lately, I started thinking about the notion of smallness, etc., which I had as calibrations, and I called these proper maps. And I realized that proper maps can be defined in a totally different manner that Bourbaki defined them. And this manner essentially amounts to saying that a proper map, say, to keep the same notation from some topological space X to some topological space I, has to be viewed as a family of compact spaces continuously indexed by the topological space I. And by using this intuition, you can prove much more than what Bourbaki proves. For example, they are stable under pullbacks, and this has to be absolutely. But there, you can. There is something like the object of a finite object k of x in a topos, where you have k of x for any topological space. By k of x, I mean the topological space of compact spaces of x. Equipped with the correct topology, you have the object of compact spaces of any space, whether it's compact or not. And it's good to use it, and this defines a triple and lots of things like that, just from the idea of compact is small in the topological spaces. So what is a family of small spaces indexed by a non-small space?
Oui, ben je parle en français.
Vas-y, vas-y.
Ce serait intéressant que tu reviennes et que tu précises encore cette question d'intrinsèque ou pas intrinsèque, par exemple dans le cas de vibration ou catégorie indexée. Parce que c'est vraiment une question de méthode dans le travail, que de savoir si quand on manipule des objets, à un moment donné, on décide qu'on est dans le cadre intrinsèque. Prenons juste un exemple. Les présentations d'objets. On a des objets qui sont considérés être là, et puis après, pour travailler dessus, on travaille avec des présentations. Alors, ces présentations, à un certain moment, acquièrent un statut d'intrinsèque aussi, dans un autre contexte. Comme par exemple, on le voyait dans les questions de la construction de la catégorie dérivée. Bon, bah, au bout d'un moment, les présentations de modules, par résolution, deviennent des objets à nouveau intrinsèques à un autre monde. Donc, pourquoi, à ton avis, c'est ça la question, pourquoi on ne peut pas admettre que les catégories indexées seraient comme des présentations de fibrations, et puis qu'à un certain moment, pour certains types de travail, eh bien, ça devient intrinsèque, peut-être dans une catégorie légèrement différente. Tu peux préciser ça?
Oui, je peux expliquer ça très simplement. Si tu prends, tant que tu restes avec une seule fibration, une seule catégorie indexée, ça n'a aucune importance, d'autant qu'il y a un théorème facile qui te dit que n'importe quelle catégorie fibrée est équivalente à une catégorie scindée, c'est-à-dire pas seulement indexée, mais un vrai foncteur. Le problème est quand tu veux définir des foncteurs cartésiens entre deux catégories indexées, c'est abominable. Tu as des trucs de cohérence à tire-larigot. D'accord? Tu peux imaginer ça. Hein, parce que les foncteurs cartésiens, tu prends une flèche cartésienne ici. Bon, donc voilà. Donc tu introduis déjà une difficulté technique ou une lourdeur technique totalement inutile. Ça, c'est une première chose. Une deuxième chose, c'est que, à partir de là, si les choses sont compliquées, et c'était le cas, on peut faire des fautes énormes. Par exemple, Johnstone et Paré ont écrit un article qui s'appelle Index Categories, etc., où ils disaient que la catégorie des catégories indexées, en prenant les bons morphismes, qui étaient très compliqués, avait des produits fibrés. Eh bien, c'est faux. Tout simplement. parce qu'on ne voyait pas que les trucs de cohérence, dans ce cas-là, ça ne marchait pas. Voilà, ils ont été amenés à énoncer un énoncé faux, parce que l'intuition des catégories indexées les a laissés en carafe, puisqu'on ne faisait jamais les vérifications de cohérence. Et bien, il y a des fois où c'est pas cohérent, et puis voilà, c'est tout. Il n'y a pas de produit fibré. Il y a des deux produits fibrés, mais il n'y a pas de produit fibré. De plus, il y a des quantités de construction qui sont extrêmement simples et importantes sur les catégories fibrées et qui deviennent compliquées sur les catégories indexées. Des adjoints, des choses comme ça devient compliqué parce qu'il faut toujours, il s'introduit des choses de cohérence qui n'ont pas leur... Et d'ailleurs, peut-être que tu as entendu, Amiens, ce que j'ai dit sur les catégories pseudo-discrètes, les vibrations pseudo-discrètes, etc. C'est un pas de plus. C'est un pas de plus parce que... Allez, on va faire bondir les gens. Qu'est-ce qui se passerait si le lemme de Yoneda n'était pas vrai? Hein? La théorie des catégories va s'effondrer ou quoi? Ah, mais le lemme de Yoneda, il n'a de sens que pour les catégories localement petites. Parce que le home X, ça doit être... Et pourquoi veux-tu me forcer, alors que beaucoup de résultats sont vrais pour des catégories quelconques, pourquoi veux-tu me forcer uniquement parce que je ne sais pas faire autrement, parce que Grothendieck a défini des foncteurs représentables et qu'il faut suivre Grothendieck? Pour une fois, Grothendieck c'est mon bon Dieu, mon grand homme, et bien je ne le suivrai pas. Voilà.
Je poserais bien encore une question.
Attends, je descends. Vas-y, je t'écoute.
Il y a un certain nombre d'années, j'avais été très intéressée par ce que tu avais appelé les points de vue, la matrice des observations, etc.
Oui.
Alors, est-ce que dans cette nouvelle théorie que l'on sent qui n'est pas si loin que ça, finalement...
Elle date de 81, hein,
oui, ça. Oui. Mais est-ce que ces choses-là que tu avais faites dans le cadre de la théorie des catégories, comment va-t-il s'insérer dans ce que l'on sent être pas très loin d'une nouvelle théorie? Est-ce que ça fera partie de l'axiomatique ou est-ce que ça en sera des conséquences comme ça l'était? Tout ce qui était la notion de point de vue, parce qu'il y a des disciplines où c'est fondamental.
Non, ça c'est l'axiomatique des catégories fibrées telles que je les vois, de la définissabilité, etc., etc., de nouveau m'a été inspiré par, comme je l'ai dit, une analyse linguistique extrêmement précise de ce qu'on faisait quand on disait si FI est un ensemble de morphismes de XI dans Y, alors on peut regarder l'ensemble des I tel que FI est un mono. On l'utilise beaucoup, bien sûr. Et premièrement, je me suis assez vite convaincu que si la théorie des ensembles ne permettait pas de faire ça, parce que j'avais moins compris ce que c'est que le schéma de compréhension. L'ensemble des X dans grand X qui vérifie phi, c'est une chose, et l'ensemble des X dans grand X qui vérifie ils ont les yeux bleus, c'est autre chose, et c'est pas un ensemble. Voilà, donc ça, c'est clair, on avait besoin de ça, ça ne résultait pas des axiomes, des autres axiomes des vibrations, on en avait besoin, il fallait poser que dans certains cas ça existait, donc ce que j'appelle les monos sont définissables. Et bon, à partir de là, les monos sont définissables, les isos. Alors on pourrait se dire, on va être obligé de faire ça pour toutes les choses. Les monos sont définissables, les isos sont définissables, les épis sont définissables, et où on va? La réponse est, si on suppose la catégorie de base suffisamment puissante, elle n'a pas besoin d'être un topos, mais bon, suffisamment riche, la définissabilité de quelques trucs bien choisis permet de montrer la définissabilité d'autres trucs importants, et donc on évalue les axiomes à nombre raisonnable, et on a toutes les définissabilités dont on a besoin, parce qu'elles se déduisent de constructions qu'on peut faire dans la base.
I just maybe final remark, just like to stress this question which René just posed about what is actually intrinsic and what is not, because my previous remark actually relates to that, because your approach of course the notion of vibration over categories, you know, kind of internalization of the notion of indexing, which is external, right? Yeah. But on the other hand, it's fibered category is not like internal category. It's not like internal topos. So it's
no, of course not.
Sort of kind of in between.
Internal categories in a topos. Yeah. That's okay. You can do a lot because you have the structure of topos. If topos is sets, it's just like looking at small categories. And for small categories, there's no problem. But the problem is, small category cannot say that it has infinite limits or whatnot. It very quickly becomes, and naive category theory is important. If we do not make category theory a first order theory, first order meaning, okay, category is first order notion. You can define a category, but a category with infinite limits, that's not first order. It's not first order. That's why my paper was not foundation of category theory, but foundation of what I call naive category theory, which is when you talk also about infinite products, or working as a categories, and not as an axiomatic-minded man, because that's not category theory. Immediately, the very first theorems on category theory will tell you if a category has infinite limits, etc., and a cogenerator, and adjoints exist. The Fried theorem on the existence of a joint immediately needs infinite limits.
Thank you very much.
Welcome.